Hi guys, in this tutorial we're going to talk about ionic bonding and ionic compounds. So first we're going to talk about how an ionic bond forms, and then we're going to talk about what an ionic compound is, and then we're going to talk about how to determine the formula of an ionic compound, and then last we are going to talk about the properties of ionic compounds. So in the last tutorial we talked about ions and how ions form. And if you remember correctly, ions can either be positively charged or they can be negatively charged. So you can have an ion with a positive charge or an ion with a negative charge. And as you can imagine, there would now be an attraction, an electrostatic attraction between those oppositely charged ions. So an ionic bond is first formed when there is a transfer of electrons between two atoms or from one atom to another. And this forms ions. Okay. So you're going to end up with a positively charged ion, which remember we called a cation, and a negatively charged ion, which we called an anion. And then, so that's the first thing that happens. And then the second thing is you end up with an electrostatic attraction between the cation and the anion. All right, so let's talk about, let's do some examples of how this is going to happen. So let's do an example using sodium and chlorine. So sodium is a metal, and it has a very low electronegativity and a low ionization energy. Chlorine is a nonmetal on the other side of the periodic table from sodium with a high ionization energy and a high electronegativity. And so what that means is that when sodium is near chlorine, sodium's one valence electron is more attracted to chlorine than it is to sodium. And so it's going to be easy to remove, because of its low ionization energy, that electron from sodium and transfer it to the chlorine. So what we end up getting is we get a sodium ion. Remember, it just lost a negative charge, so it's going to end up positively charged. And we get a chloride ion. So if we draw the Lewis dot structure for what just happened to chlorine, chlorine picked up sodium's extra electron, and now it has a -1 charge because it just picked up an electron. So we've got a sodium ion and a chloride ion. So now that the ions have formed and they have opposite charges, so a +1 and a -1 charge, those oppositely charged particles are going to be attracted to each other, and you're going to end up forming sodium chloride. So we've just made, or rather written, the formula or the process for making sodium chloride. Okay, let's try one that's a little more complicated than sodium chloride. Okay, so again, we have our metal and our nonmetal. If you remember, metals have a low ionization energy or electronegativity, and sulfur has also, or rather our nonmetal has a high electronegativity and ionization energy. So that means that the electrons on calcium, its valence electrons, are more attracted to sulfur than they are to the calcium. So in this case, it's going to lose both of its electrons to the sulfur. And now you'll notice, though, that sulfur needs 2 electrons. It's got 6 valence electrons, and it needs 2. So this works out really great for the two of these guys, because calcium is going to end up losing 2 electrons and ending up with a +2 charge because it just lost 2 negative charges. Sulfur ends up with a -2 charge because it just picked up 2 electrons from the calcium, like so. And you end up forming calcium sulfide. So 1 calcium to 1 sulfur, and this is called calcium sulfide. Okay, so something I want to point out that, in our last example, our positive and our negative charges were exactly equal in magnitude, meaning they both were 1, and then exactly opposite in charges, so +1 and -1. And the same thing was true here. Our charges were exactly equal in magnitude, 2 and 2, and then exactly opposite in charge, plus and minus. So it worked out perfectly that we would get 1 calcium and 1 sulfur being able to do an electron transfer, and everyone ended up with their octet, and they were very happy this way. This isn't always as easy as it seems. All right, let's do a little bit more complicated one. So here we have calcium and we have phosphorus. Now you'll notice that calcium has 2 valence electrons to give, and if it gave those electrons away, because it's a metal, it's going to do that, it would end up perfectly happy. It would end up gaining its octet or with its octet. Whereas phosphide has 5 valence electrons, therefore it needs 3 more to complete its octet. But you'll notice calcium only has 2 valence electrons, not the 3 that phosphorus needs. So phosphorus isn't going to be happy unless it gets all 3 of its valence electrons, and so 1 calcium atom is not going to work for phosphorus. So how can we make this happen so that phosphorus can get all of the electrons that it needs, and calcium can get rid of all of its valence electrons so that they both end up being stable and getting their octet? So what that means is that we're going to need more than 1 calcium atom, and we're going to need more than 1 phosphorus atom involved in this reaction. So it doesn't have to just be a 1-to-1. It can be more than 1 of each kind of atom. So watch what happens here. So our calcium can get rid of, one of our calciums can get rid of 2 of its valence electrons and end up happy. And then the other calciums can also give up their valence electrons and end up happy. And then this third calcium will lose its valence electrons and end up happy. So in this case, you had 3 calcium atoms giving up each of its electrons to 2 phosphoruses. So you end up with 3 calcium ions and 2 phosphorus ions. So another way to write that is 3 calcium ions to 2 phosphorus or phosphide ions. And then, of course, because of the opposite charges, and because that we have an opposite charge of, 3 times +2 is a +6, and 2 times -3 is a -6. So we have equal and opposite charges. We're going to end up forming the compound from 3 calciums and 2 phosphides, the compound calcium phosphide. So you might want to write down that electron transfer is only going to occur if every atom involved gets its octet. So sometimes you're going to need more than 1 of each kind of atom to ensure that everyone gets an octet. Okay, so let's talk about what an ionic compound is. Let's define an ionic compound, since you've now seen how an ionic compound would form. So an ionic compound is a compound formed by the electrostatic attraction of oppositely charged ions. So electrostatic attraction, just remember, that's just a magnetic attraction where oppositely charged things are attracted to one another. And so it should be noted that an ionic compound is always made of a cation and an anion, so oppositely charged ions, that they are always neutral in charge. So what that means is that when the ions come together, their charges cancel out, and then the compound ends up being completely neutral in charge. You should also know that when we talk about an ionic compound, we sometimes call them salts. So just know that that's another word for an ionic compound, is to call it a salt. So whenever we talk about salts, we mean any ionically bonded compound. And then one last thing that you might want to also take note of, that the simplest unit for an ionic compound is called a formula unit. So I guess what I mean by that is that, we have molecules, like if you have one water molecule, it's just one water, two hydrogens, one oxygen bonded together. When something's ionically bonded, we don't call them molecules. Instead, we refer to them as formula units. Okay, so let's talk about how you can determine the formula for an ionic compound. Because, this, as fun as it was to draw this picture to figure out the formula for calcium phosphide, it seems a little like a lot of work, right? There seems like there should be an easier way to do that. And in fact, there is an easier way. So of course, the easier way relies on you being able to determine the charge on the ion without drawing pictures. So remember, you can determine the charge on an ion by looking at the family that the element is in. So calcium's in family 2, and we know that because it's a metal, it's going to lose those 2 electrons and end up with a +2 charge. Phosphorus, on the other hand, phosphorus is in family 15, which means that it has 5 valence electrons. And it's a nonmetal, so instead of losing electrons, it will gain electrons. And so, of course, it has to gain 3 to end up with its octet, because it has 5 and it wants 8, so it's got to gain 3, and it's going to end up with a -3 charge. So once you're able to assign charges to ions, figuring out the formula is super simple. It's just a matter of taking the numbers here and crossing them down. They call this crossing the charges. And all this really does for you is make it so that you can figure out the formula for the compound. So we take that calcium and we take the 3 that we cross down, and that phosphorus and put the 2 that we cross down, and this gives us the formula for calcium phosphide. All right, let's do another example. So here we have potassium with a +1 charge and oxygen with a -2 charge. Again, you should be able to figure out the charges from where they're located on the periodic table. And if we're going to try to figure out the formula for our potassium and our oxygen compound, we're just going to take these numbers, don't take the charges, just the numbers, and you're going to cross them. So you're going to end up on the other side, or rather you're going to end up forming a compound with 2 potassiums, right, because we put the number here, and 1 oxygen. Now, there is a 1, but you don't write the 1 if you don't need to, because obviously if we listed oxygen at all, there must at least be a 1. So you don't have to put the 1 here. It's not appropriate to put the 1 there, so don't put the 1 there. So K2O is potassium oxide. But I hope you're paying attention a little bit at least to the way we're naming these. They always end in "ide." All right, so let's talk about the last thing, what the properties of an ionic compound are. So because these ions are oppositely charged, what ends up happening is that ionic compound, the ions end up setting themselves up into what's called a crystalline structure. So they take on a crystal structure. So all ionic compounds are crystals. And the reason that happens is you want to, maximize the attractive forces between the oppositely charged particles, while sort of minimizing the forces of, repulsion between the same charged particles, right? So you want them to, so for that reason, they set up into a nice crystal structure or crystal pattern. You also should know that ionic bonds are pretty strong, right? The bond is a pretty strong attraction. And so for that reason, and for this crystal, because there's this crystal structure at all times, they tend to be solids at room temperature. So they're never liquids at room temperature. In fact, if you want to liquefy or melt an ionic compound, you would have to heat them to very high temperatures. They have very high melting points. So just to give you an example of how high these melting points are, sodium chloride melts at 801 degrees Celsius. So if you figure water melts at 0 degrees Celsius, that's really high. Or if you're used to using Fahrenheit, that's 1,474 degrees Fahrenheit. That's really, really high melting point. Another property of ionic compounds is that a lot of them are soluble in water. Not all, but most are soluble in water. So, there are definitely exceptions to the rule, but for our purposes, we're going to go ahead and say that most of them are soluble in water. Okay, and then when they are, so as their solid form, they do not conduct electricity. And, you can really figure out why, because, the ion charges are all canceling each other out, and so it's a neutral substance. But when dissolved in water, so when in solution is what we call that, so in solution means dissolved in water, they do conduct electricity. And that's because when you dissolve them in water, the ions will separate. So you'll get for example here, your chloride ions will separate from your sodium ions. So they're just kind of floating around separate from each other. And then an electrical current can kind of jump between the ions. All right, so that brings us to the end of our presentation on ionic bonding. I hope you enjoyed.